Good morning. This is the second and last video for chapter 3. This one's going to be on periodic trends. You will need your periodic table, so make sure you either have it pulled up or it's out, okay? All right, so we kind of already talked about effective nuclear charge, and just remember that's the pull of the electrons from the protons, so from the nucleus. That's why it's effective nuclear charge. Okay, also, effective nuclear charge will increase as you go across a period this way to the right. It will also increase as you go up. It says decreases, but I don't like those arrows. Okay, so effective nuclear charge is going to be highest at helium because on the periodic table, that's where we're pointing, closest to helium. Okay, and just remember, ZEF is the abbreviation for effective nuclear charge. Okay, and it's about the atomic number minus those valence electrons. Which remember you can find from the A's or the B's. Sorry, these are core electrons, not valence. Which you find from subtracting the total minus its valence, okay? So here it wants to know which atoms' valence electrons experience the greatest effective nuclear charge. And remember, it is highest at helium. So the arrows point towards helium. So really you're just looking which one of these is closest to helium, and it is sulfur. Okay, magnesium will be the farthest. Radius is next. The atomic radius trends are opposite. So we'll talk about that in a minute. And just the radius is from the center of an atom to the outside. That's what normal radius is, from the center of a circle to the outside. Here it's doing half of from two centers of atoms, which is essentially the same thing if they're together. Okay, these arrows, again, point the opposite way, and they talk about decreasing. I only like increasing arrows. So FR is the largest. That is the largest atom on the periodic table, francium, down here at the bottom, number 87. Okay, the reason that one is the biggest, because as we go down the periodic table, if we're looking at the Bohr models, they're getting bigger because we're adding shells, those energy levels. So it makes sense that as we go down, they get larger. As we go across the periodic table, that effective nuclear charge increases, which is the pull of the electrons. So when you're pulling something, you're pulling it closer to you. And so they get smaller as they go across. Okay, valence electrons. The larger the effective nuclear charge, the smaller it will be. Okay, so again, atomic radii is opposite of effective nuclear charge. So, of the pair, which one is larger, nitrogen or fluorine? So it's going to be nitrogen because it's closer to the left-hand side of the periodic table. Carbon or germanium, that one's going to be germanium because it's farther down. Nitrogen or aluminum, it's going to be aluminum. Not only is it farther down, but it's also closer to the left. And then aluminum and germanium, they're going to say you can't tell. And I'll show you. It has to do with where they're located. So the diagonal for, because the arrows point towards francium, goes to the bottom left. And because they're opposite that diagonal, you cannot tell. So I won't ask you any like that on quizzes or tests. All right, let's do one more practice set. Tin or iodine. Tin is closer to the left. Germanium or polonium. That one's going to be can't tell. I'm going to put a question mark. Chromium or tungsten is going to be tungsten. It's more towards the bottom. Sorry, my dogs are playing. They're being a little loud. And selenium or fluorine, it's going to be selenium. It's farther down and farther to the left. Okay, now it wants us to arrange them in decreasing radius. So that means smallest is last and the largest is first. So we're looking for the one closest to francium first. which is rubidium. So Rb is the greatest. And then calcium. Calliope. No, ma'am. And then silicon. Sulfur. And fluorine. Fluorine is almost the smallest element because it's closest to helium. Okay, so if you have to arrange them, just make sure you know which one it's asking. Is it increasing or decreasing? Decreasing means biggest to smallest. Okay, let's just real quickly talk about para and diamagnetism. Paramagnetism is when there's unpaired electrons. So here we've got this unpaired electron. On diamagnetism, everything is paired, and you must do this from orbital diagram, which means the arrows. You cannot tell unless all the orbital diagram is filled in. Okay, so if you need help with that, please let me know. I'll be happy to send you extra practice. So here it wants to know if they're paramagnetic or diamagnetic. It does want us to do the electron configuration and the orbital diagram because you can't do it without. Okay, so let's do aluminum 3+. We did talk about doing this for ions a little bit, but we're just going to remember. Remember, 3+ means it lost 3 electrons. So aluminum is element 13. It'll look like element 10 because it lost 3. So it's 1s2, 2s2, 2p6. That is element 10, which is neon. Got 1s. All right. This is diamagnetic. Yep. Because everything is paired. Okay, let's look at S2 minus. So 2 minus means it gained 2. We look like argon. Okay, 1s, 2s, 2p, 3s, 3p. Everything is full here, so this one is also going to be diamagnetic. But it's good to practice that we're filling everything in the correct way according to Hund's rule, Aufbau, and Pauli exclusion. Iron is different. Okay, so, that's not what I wanted. Well, we can go to the next page. Okay, so it wants iron 3+, but because iron is a transition metal, I want to do normal iron first. So normal iron, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Okay, remember when you've got transition metals, they're going to lose valence electrons first. Really, they lose all valence electrons first. Every element does. But transition metals are a little different. Okay, so we're going to do 1s2, 2s2, 2p6, 3s2, 3p6. We're going to write 3d because I got rid of these two. And this one needs to go down to a 4 because it lost 3 electrons. Okay, so when I do the orbital diagram, everything is full except the last section, which is normal. Up, 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 up. I do want to be very clear that notice we've got this empty one, but you still have to write that empty one because D could hold 5 orbitals or 10 electrons. Okay, you have to draw them all out. So this one is paramagnetic because it has those unpaired electrons. If you would like more practice, there's some here. And then, of course, I have extra if you would like. You just got to email me. Okay, so now we're going to talk about radius of ions after we just talked about ions. So effective nuclear charge is going to play a role in it. If you notice here, all the cations, the ones on the right, are smaller than the atom. So you need to know that cations are smaller, and it's because they lost electrons. It's just like if you lose weight. If you lose weight, you lose some size, and if you lose electrons, you lose some size. Okay, anions are the opposite, which is pretty common. Cations and anions are opposite. They will get electrons added, which means they become larger. Anions are going to get larger than the atom. Okay, so just some things to remember. Cations are smaller than anions because they lose stuff. Cations are smaller than their neutral atom. Anions are going to be larger because they're gaining. Also, the larger the positive charge, the smaller it is. And the larger the negative charge, the bigger it is. Okay, I do want to talk about isoelectric because I am going to start using that term. Isoelectric means they have the same electron configuration. So when we just did aluminum 3+, remember I said it lost 3, so it looks like it has 10 electrons. So it's isoelectric with neon because according to its electrons, it looks like neon. So here we're going to say which one is larger. Remember, anions are larger than cations or neutral. Cations are smaller than their atom. And here we're looking at Br minus and Kr. They are isoelectric with each other. The anion will be larger because it gained stuff, so it gets bigger. Okay? Krypton is neutral, and so it is the size it's supposed to be. But when I add extra stuff to bromine, it's going to get bigger than it normally is. Okay, what about potassium and potassium plus? It's going to be potassium because the atom is larger for cations. For fluorine, the anion is larger than the atom. And for calcium and chlorine, those are both isoelectric with argon. The anion will always be larger if there's an anion and a cation that are isoelectric with one another. Okay, ionization energy is the next trend we're talking about. It is the same arrows as Zeph. So these arrows are for Zeph and ionization energy. Okay, ionization energy's definition is that's the minimum energy needed to remove an electron from the atom. So when you think about it, the noble gases are going to have the highest ionization energy, and that's because they really, really, really don't want to give up any electrons. If you pull an electron from a noble gas, it's going to take a ton of energy. So here you can see in the graph that all of the noble gases are the highest point in each row. Metals are going to be lower because they're going to want to easily give up electrons, so they don't have as high of energy to remove them. Okay, so that larger effective charge, the more energy it takes, and the farther the electron is from the nucleus, the less energy it takes to remove. So that's why as you go down, they get more easy, and that's because they're farther and farther away from the nucleus, so that pull is not as strong. Okay, this is just another image of the trend. Okay, so again, arrows look like this. Those are increasing arrows. I do not like decreasing arrows. So aluminum and sulfur, it will be sulfur. Antimony and arsenic, it will be arsenic. Nitrogen and silicon, it will be nitrogen. Oxygen and chlorine is a can't tell. It's got that weird diagonal. And you can see that diagonal there because these are pointing up and to the right. Tin or iodine? Iodine, they're in the same period. Calcium and strontium, it's going to be calcium. Carbon and phosphorus is that we don't know. It's that weird diagonal. And fluorine and sulfur is fluorine. Now we're going to arrange them in decreasing ionization energy, which means the biggest ionization energy goes first, which is fluorine. And then sulfur, and then silicon, then calcium, and rubidium. Again, please let me know if you need help with this. I'll be happy to send practice over. Okay, there are some exceptions. I'm not going to test any exceptions, but they may come up on a homework question. Okay, so here we've got beryllium and boron. Notice the one electron here and then the empty electrons for beryllium. Okay, boron's is going to be smaller ionization energy than beryllium. Okay, and that's because beryllium is full. It's got that paired, and so it's easier to pull off one electron from boron than it is to pull off two. So that S and P difference, if there's only one in P, that one will have lower ionization energy, even though it's closer to helium. Okay, also with half shells. So nitrogen has a half shell, oxygen has more than a half shell full. So oxygen will lose easier than nitrogen, and that's because nitrogen doesn't have any repulsion here, but oxygen has this repulsion there. Lively weight. Okay, there's also second and third ionization energy. So the second ionization energy is pulling off the second electron. The third ionization energy will be pulling off the third electron. Notice, first ionization energy is always the smallest down here, regardless of how high the ionization energy is. When you see the very large jump, that's how many valence electrons they have. So here we've got one valence, and here we've got two valence. Okay, and just remember, ionization energy is still always going to increase. Those noble gases will have the highest energy. So sodium looks like a noble gas after one is lost. Magnesium looks like a noble gas after two are lost. Aluminum will look like a noble gas. See the big jump from here to here? So you will need to be able to recognize the big jump. Stop, y'all. Sorry, my dogs are playing, and I'm about to go put them in another room. Okay, so just look for the big jump. That's how many valence electrons it has. Just remember some characteristics of metals. Metals are malleable, which means we can flatten them into sheets. They're ductile. They can be drawn into wires. They're shiny or lustrous, and they will reflect light. They'll conduct heat and electricity, and they will form those cations. Nonmetals are exactly the opposite. So they're brittle in their solid state. They're dull and non-reflective. They are insulators of heat and electricity, and they will form anions. So the last thing for this chapter is metallic character. The metallic character arrows look just like the atomic radius arrows. And this is how closely they have properties to a metal. So even nonmetals have some metallic character, and as they get closer to the metal section, they're going to have more metallic character. So again, don't like the decreasing arrows, so it goes this way as it increases, the opposite direction. All right, this is just some common things we've already talked about. So again, arrows point to francium. So there's two sets of arrows, tin and tellurium. We're looking at tin being more metallic. When you look at it, tin is a metalloid, tin is a metal, tellurium is a metalloid. So because of that, it would make sense that the metal has more metallic character. Between phosphorus and antimony is lower. Okay, germanium and indium, it's going to be indium. And then sulfur and bromine is we don't know because of the diagonal. Also, they're both true nonmetal, so it's harder to tell. Germanium and tin. Gallium and tin is I don't know. Phosphorus and bismuth. And then boron and nitrogen. Okay, increasing metallic character, so the one closest to francium is going to be last. So it's chlorine is the smallest, and then silicon, and then sodium, and rubidium. Rubidium will be the largest. Okay, here is a summary of all of it, but again, remember atomic radius, those arrows, ionization energy. We didn't actually do electron affinity, but this is Zeph. So they point towards helium. The metallic character is just like the atomic radius. Okay, y'all have a great day. I'll talk to y'all again when we do chapter 4.